Hi, welcome to this lesson on calculus, the second derivative. Let's have a look at what an inflection point is. So we start off with the definition that f be a function. Then f is said to have an inflection point at the point x, if and only if the second derivative at that point x is equals to 0. So what's happening graphically is that the function f is changing concavity. That's really important. But an inflection point on its own doesn't just rely on the fact that its second derivative is equal to 0. The concavity must also change on the left and the right of that inflection point. So it can either change from concave up to concave down, or vice versa, from concave down to concave up at that point of inflection. So mathematically, the second derivative is 0, and it has the following shape. So we can see here the tangent lines are above the graph, so the graph is down from the tangent lines. So this entire blue is concave down, which I'll just call CD for short. And then the red intervals, because the tangent lines lie below it, so the graph is above, it's up from the tangent lines, that's concave up. And then similarly again, the tangent lines are above here, so the graph is lying below the tangent line, so it's concave down here. Okay, so you can see that at this green point here, it changes from concave down to concave up. And then at the second green point here, it changes from concave up to concave down. So at those points, the second derivative will be equal to 0. And because they are changing concavity at that point, we say that those 2 points there are points of inflection. So you can sort of think about the analogous interpretation of the first derivative, where if you look at a function, it increases, reaches a turning point, and then decreases again. The first derivative here was positive, right? Then this first derivative was equal to 0 at the stationary point, and then the gradient lines had negative gradients here. So the first derivative was less than 0. So it's a similar idea with the second derivatives now, but instead of talking about increasing, decreasing, and stationary, we're talking about concave up, changing inflection, concave down, or concave down, changing inflection, concave up. Okay, so very similar analogies to each of the first and second derivatives, but they tell us a different picture for each derivative. The first derivative tells us how the graph increases, turns, and decreases, and the second derivative tells us in what bendy direction does the graph increase and decrease and change that bendy direction. Okay, so putting all this information together with the first derivative and the second derivative, let's have a look at some questions and making sure that we keep our eye on the main goal, and that is we are using all this theory and terminology towards applying it to sketch cubic functions. Okay, I'll see you in the next one.